So this is the very last bit of your Advanced Higher Physics course, and it's to do with the last bit of electromagnetism, and it is the idea of electromagnetic waves. So an electromagnetic wave, as we're going to see, involves both electric and magnetic fields. We know that much from polarization. It originates from some disruption, either a high voltage or spark or something which will cause a very strong electric and magnetic field there. It's got wavelengths, it's sinusoidal, as you can see there. It's a couple of nice simulations I want to show you. The first one is quite nice because you can see exactly what's going on here. You've got the two field vectors, so the electric field here is shown in the vertical plane, magnetic field in the horizontal, and it's all traveling at a nice relaxed rate. Slightly better is this one here, where you can see the actual planes of the electric field there and start going there. And you can see the electric field is increasing and decreasing, so it's causing that wave to move along like that. There. Can put in the magnetic field plane perpendicular to that, and the magnetic field component. So the maximum amplitude happens at the same time for both and moves along at the speed of light. So the key thing here again with polarization is the two fields are in planes. The direction is the direction of propagation or travel of the wave. So you've got to be really careful when you're explaining that you refer to planes as opposed to direction. It's a fitting end to your Advanced Higher Physics course in that the person who brought together all the ideas of electromagnetic radiation was James Clerk Maxwell. This is his house down near Edinburgh, and these were his equations. Tremendous. Good news is you don't need to know them for Advanced Higher Physics. There's obviously a lot of calculus in there. I don't understand them because I didn't do a pure physics degree, and there's bits and pieces that I do know of from electromagnetism in my engineering degree, Gauss's law and Ampere's law, Faraday's law. But what he did is he tied the whole thing together, and it's summarized for you for Advanced Higher in this equation, which you do need to be able to use. But it's the easiest equation ever in some respects because you're given both things in the question paper. So you're given both of these constants, you know you are, and all you would ever be asked to do is to work out the speed of light by substituting in the permittivity of free space and the permeability of free space, and you always get the same number. How easy is that? So that's your one equation, and that is what actually defines the speed of light in terms of those two constants. So hence, in a vacuum, and it's important that it is in a vacuum, the speed of light is always constant because it's based on two constants. So this is what you need to know. Just that electricity and magnetism are unified for electromagnetic radiation. We'll come back to this one along here, and then the appropriate relationship to solve problems involving the speed of light, permittivity and permeability. Yeah, what problems can you get with that? Key terms here. Okay, so electromagnetic radiation exhibits wave properties, so it is a wave, or it has wave properties as well as particle properties at some points, and transfers energy through space, no problem there, has both electric and magnetic field components, and they oscillate in phase, so they're both doing the same thing at the same time, and they're perpendicular to each other and to the direction of that propagation of the energy. So really importantly, use these words, these keywords in there in the right way, because that's what SQA are actually putting into their outcomes. Okay, so that's it. Course done. Electromagnetic radiation, nice one to end with, and there's a few questions still to do.